A rectangle is inscribed within the parabola y equals 18 minus 0.5x squared, with its base on the x-axis, one side along the y-axis, and one corner on the graph of the parabola. We're going to begin by sketching three possible diagrams of this scenario. So let's begin by thinking about what this quadratic function would look like. So that we could graph our parabola. So I'll go ahead and make an x-axis. I'm going to make a y-axis here. And you want to recognize that your y-intercept is at 18. You'll also want to recognize that this parabola opens down due to that negative leading coefficient. The leading coefficient is negative 0.5, the coefficient of the quadratic term. So we know we're going to have a parabola that looks like this. Okay, so let's also go ahead and determine for this parabola where our x-intercepts are. For our x-intercepts, if I substitute 0 in for the y and I solve for x, I could subtract 18. This is one way to solve for x. Divide by negative 0.5, I'll get 36. Take the square root, not forgetting my plus or minus. I will have two x-intercepts, negative 6 and positive 6. And now to bring the rectangle into this diagram, it says that the rectangle that's inscribed in this parabola will have a base on the x-axis, one side along the y-axis, and one corner of the graph on the graph of the parabola. So this is one possible scenario. Let's just say that this point here, xy, will be a corner of our rectangle. And bringing in the other constraints, we know that we want one side to be along the y-axis, and then we want one side along the x-axis. So I'll draw it to there since that's where I'm placing my point, there. And my goal is going to be, if I look ahead to part B, to write a function that models the area of all such rectangles. So remember, this is only one possible diagram. So I'm going to go ahead and shade this in because ultimately my function that I come up with is going to be about area. So now since I want three possible diagrams, we can draw two more possibilities, essentially putting this point xy in a different location to draw two more diagrams where you have a rectangle inscribed within this parabola and have them be slightly different by moving the location of that XY point. You can pause the video to do that and then come on back. Here are three possible diagrams of this scenario. Again, as described before, with a point, a corner of the rectangle being on the graph of the parabola, one side of the rectangle being along the y-axis, and one side being along the x-axis, so the base being along the x-axis. Now let's focus on writing a function of a single variable that models the area of all such rectangles, and then we'll look at what is the domain of that function. So if we think about how do we find the area of a rectangle, hopefully we recall that to find the area of a rectangle, it is length times width or base times height. Now, it's important to note that when we look at our current scenario, we have two variables. We have x and y. So if I go pick any one of these diagrams, this distance here would be x, this distance here would be y, and to find the area, that would be x times y. But the problem is right now I have two different variables. And if you notice in the directions, it says we want a single variable. So if I want a single variable, I have to think about this y right here and recognize that y is equal to this 18 minus 0.5x squared in the problem. So what I could do is I could do a substitution for that y, since y is the same as 18 minus 0.5x squared. And then I could distribute that x so that I end up with (18x minus 0.5x cubed). And if I wanted to bring in my function notation, area could be a, and my input is x, so a of x equals 18x minus 0.5x cubed. That could be my area function using proper function notation where x represents the length of the base. This part also asks us to determine the domain of the function. So we definitely want to think of the domain in the context of this problem. And if we look at our rectangles here in part A, we'll notice that our base needs to be, well, first of all, our base needs to be a positive length, okay? So if our base needs to be a positive length, and we could technically, if we wanted, make our rectangle, you know, long this way, right? Our x-intercept would be necessary for our upper extreme of the context. And if we included 0 or included 6, the issue there is we wouldn't be able to get a rectangle. So I'm going to go ahead and say that the domain in the context of this problem is going to be 0 to 6, not including 0 and not including 6. So this here would be the domain, again, within the context of this problem. In letter C, it says what value of x will give the largest rectangle possible. In order to do this, we are going to want to use our graphing calculator. Okay, and while we're using our graphing calculator, our goal is going to be to calculate the max. And really, once we calculate the max, that's going to actually help us answer part C and part D. So if we turn on our calculators, we're going to want to hit y equals. We will put in our function 18x minus 0.5x and hit the caret cube. Okay, and that will enter our function, and then to graph it, we are going to want to adjust the window. If you want to hit graph, you can see what it looks like right now. But we want to keep in mind that we have stated that our domain is from 0 to 6. So we really only want to see a certain portion of this graph. So if I go to window, I'm going to go ahead and change my minimum to 0 and my maximum for my x values to 6. And then for my y min, it doesn't really need to go all the way down to -10. We could start that at 0. And if you recall, for the quadratic function, the parabola, our y-intercept was 18. So actually, maybe we should just go ahead and make that an even 20. If we want to change our scale, maybe we want to count our tick marks by 2, then we can go ahead and hit graph. And again, if you'll notice here, that's still probably not a good picture because I was only considering the quadratic function. But really, what I have is a cubic function, and I'm trying to graph the area model. So you can see if you look here at the top of the graph, you can't see the maximum value. So we need to go a little higher. So there's different methods in adjusting your window. One feature you can use is the table. If you go second graph, it takes you to a table and you can look at your Y values here and I can see, oh, my Y values, they go all the way up into the 40s. So just looking at the parabola is not enough. Okay, so again, it can be like trial and error, but you're not gonna mess up your window and you can always go zoom 6 to get it back to a standard window and then work with it from there. So you can keep adjusting your window. So initially what I looked at was just the parabola, but looking at the area function, I now know that I want to go up higher than the table said 40, but that didn't include every value. So maybe let's try 50. We can maybe count by fives now. Let's hit graph. So as long as, again, I'm going to go back to my window so you can see that because I went kind of quick. My x min is 0. My x max is 6. That satisfies my domain. And then I played around with my y max the first time, only considering the parabola. And what happened there is I didn't have a good enough picture to see the maximum in my window. So I went to my table and saw, oh, my y values, they go up into the 40s. So let me go ahead and increase that y max. Now you can see, yes, indeed, I have the maximum in the picture. So to calculate that maximum, I'm going to go second trace, and you'll see you can calculate just a value where you pick an x, a 0, which is an x-intercept. You can calculate a minimum, in this case a maximum. If you have two curves, you could use this menu to calculate where two curves intersect. But I am going to go ahead and go to the maximum because that's my goal for now. And then you'll see a little blinking cursor. You want that to be to the left side of the maximum. Hit enter. Depending on what model of the calculator you have, you might see a little arrow there, or there might be like a little dotted line if you have one of those fancy colored screens. And then what I'll do is I'll arrow over to, it says right bound, to the right side of that maximum. I'll hit enter again. You should see two little arrows or two lines. So the two arrows would be pointing into each other. It will say guess if you want to give it a shot. Otherwise, you can just hit enter and it will calculate the maximum for you. So let's say for our purposes, let's go ahead and round 2 decimal places. So the x value of 3.46 would represent the largest possible x value, the x value that will give us the largest possible area. Okay, so the largest rectangle possible, the value of x is 3.46. And then the maximum area, so the largest area possible given this scenario, would be the y value of 41.57. So going back here to letters C and D, let's recognize that our maximum point is about 3.46. 41.57. So this is our x value, and this second value is our area. So for letter C, we're looking for the value of x that gives the largest rectangle possible. That would be x is approximately 3.46. Just to make sure we answer the questions that are at hand. And then in letter D, we are looking for the area. The maximum area is that 41.57. Now typically there could be units here where area is square units, and the length of the base would be linear units. In this case we don't have any units, so just giving the value itself is sufficient.